Okay, good morning, everyone. Thank you for joining us for this webinar on Beaver Dam analogs and post-assisted log structures. I hope you've all signed into the webinar okay. I know there are still a few registrants who have not signed on yet, so hopefully they'll be able to do so soon. My name is Anna Freitas. I'm the Policy and Program Manager for the Oregon Association of Conservation Districts, and I'm going to be moderating the presentation today. This webinar is part of a monthly webinar series from the Oregon Conservation Partnership. We use this forum for training and information exchange for soil and water conservation districts, watershed councils, and land trusts in Oregon, but we welcome other partners and folks from out of state as well. These webinars are offered in support from Pacific Corrugated Pipe, a company in Eugene, and the Oregon Watershed Enhancement Board. We sincerely thank them for their critical support in helping us offer this resource for you all. We have 22 people registered. Not quite everyone has signed in yet, but joining late is also okay. In a minute, I'm going to hand it over to our presenter, Dr. Chris Jordan from NOAA. But first, a couple of housekeeping items. You are all muted by default, and I will also mute myself while Dr. Jordan is presenting. But there are a couple of ways you can participate in the webinar. You can type a question in the question box, and I'll keep an eye on those throughout the webinar, and Dr. Jordan will find some convenient stopping places when we can ask those questions. If you want to say something or ask a question that we can all hear, you can raise your little hand icon and I will unmute you either at those convenient stopping places if there's time, or at the end of the presentation. You can lower your hand again after you ask your question too, so I don't unmute you unnecessarily. You'll see there's a handout that you can download. That is Dr. Jordan's PowerPoint presentation. The recording and the handout will be posted on the Oregon Conservation Partnership website after the webinar. There will also be 3 polls throughout the webinar where we'll ask you questions along the way. You'll see a little window pop up and I'll give you about half a minute to answer those short questions. The next webinar is July 18th at 10 a.m. as always. This one is titled Your OWeb Grant from Start to Finish. And I'm really looking forward to learning from that one. There's also a short survey at the end of this webinar where you can give some feedback and suggest future webinar topics. If you would like to receive information on upcoming webinars, please include your name and email address somewhere in the survey. There are a couple open response questions in there, and you can just put it in there at the end of your response. And lastly, this webinar is being recorded, and as I mentioned, it will be on the Oregon Conservation Partnership webinar. Feel free to share the link with colleagues who couldn't make it today. So with that, let's get started, and I will hand it over to Dr. Chris Jordan.
Oops, sorry. Sorry, I had my camera on and my audio on mute. Anyway, so let me start the introduction again. I'm going to not have this web camera up the entire time so that you can see the screen, but I just wanted to say good morning and apologize that this is not as more interactive, but as you heard, we do have a couple ways you can interact in terms of polls, and then I'll pause for questions a couple times during the presentation. If there's problems with the audio or internet connection, please raise your hand through the chat or the questions so that I can find out and I can pause to make sure that there's not that disconnect. All right, so let me close out the camera and get going. So I want to talk today about what I call Beaver inspired stream restoration. And this is work that I've been doing with a whole list of partners here from Utah State, from a number of consulting companies, South Fork Research, Ecological Research, other colleagues at NOAA, many other folks involved from state and federal agencies. But most critically, this is work that we've done on the ground, private landowners, federal lands, and working in conjunction with watershed council, soil and water conservation districts. So what we're all here to, in our work, is to talk about stream restoration. And that stream restoration issue is pretty simple to state in that the scale at which stream impairment and riparian degradation is enormous across the entire U.S. And even though the sort of restoration industrial complex spends billions of dollars a year doing stream restoration, we're really just scratching the surface in terms of the numbers of stream miles addressed. Often because large, expensive projects on large rivers are the focus of a lot of the spending, but as a result, that leaves a lot of miles of streams neglected, just because most of the stream network are small streams that maybe those large approaches aren't necessary. And so we end up with having a lot of the stream network across the whole U.S. that looks like this, easily identifiable as degraded in lots of different ways. And what we've lost is this, much more functioning, intact stream systems that have all of the natural processes that make up all of the physical and biological characteristics that we know of aquatic habitat. So the question is, from a stream restoration standpoint, how do we go from this degraded condition, A, to B, the what we think of as an intact, right? What does an intact stream look like? So what are your targets for restoration? What are your characteristics that you would give to a restoration design or a restoration practitioner? So that's sort of our first task, is to ask, looking at a stream, is it in good condition or in bad condition? So if it's in good condition, then you're tempted not to do anything. If it's in bad condition, then you're going to do something. And so this comes to our first poll. I want you to look at this stream reach for a second, and then I'm going to ask you, as a poll, we're going to ask you to say, is this in good condition or bad condition? So apply your lens of what you understand about functioning stream systems, the appearance of them. Look for the indicator that you use to judge good or bad, or the suite of indicators, and now share that with everybody. So here's our first poll. So is that stream reach in that picture in good condition or bad? So you have 30 seconds or so. I'm not giving you a middle ground. You got to commit, good or bad. All right. People voted. So to be able to answer that, to think about that, and hopefully the collective answers will pop up on the screen. You have to be able to see what the stream condition is. So 75% of you said it was in bad condition. And so the kind of things that you might keyed in on is a lack of riparian vegetation. It looks very simple. The other things that I'd like you to think about, and maybe some of you grabbed this and some of you didn't, is what's the appropriate form for the channel in this place? So here's what the river actually did with that restoration project. So this stream form was a restored channel. A lot of money was spent to make this form, which looks like, sort of in our mind's eye, an appropriate stream channel. It's got sinuosity, but for this particular place, the gradient and the bed material, it's an alluvial fan. A multi-threaded, very mobile channel is the desired condition, and the stream took care of that itself, right? And this is what happened to that restoration project, because that channel form was not appropriate. And so when thinking about restoration, it's really necessary to understand what the natural processes are, and what the stream sort of desired natural condition is, since the river will be fighting you in every sense if you haven't gotten that right. And so what we're talking about is often restoration is an engineering problem, with is approached as an engineering problem with very detailed designs, and the engineering criteria is stability. It's not going to be a gaining or a losing reach in terms of sediment, in terms of water, and habitat. We think of as habitat features like pools and riffles are actually constructed so that in a grading plan or a design, the idea is to put in particular habitat features. And there certainly are places where this kind of approach is appropriate. So in places where very dynamic things, rivers, exist near lots of infrastructure, needing to control what that system does is appropriate. But in maybe a more less sort of infrastructure potentially impacting area, as in this picture here, then constructing habitat means that you are building something that may be inappropriate. And as a result, it's a high cost per mile, which means you can do less of this restoration. And so you end up with this tension between what's the reason for doing and that is you see an impairment, and what's the approach, that is how do you approach the design and the implementation of restoration. So what has come, the language to try to address that in the restoration in the science world that's come to the front in the last 15, 20 years or so, is process-based restoration. So it's the direct alternative to constructing features. So the process impairment is the root cause of the problem, not just the impairment itself. And the restoration, adjusting that process, has to be consistent with the site. We saw an example of that with a reach that didn't want to be in a single channel because of its gradient, because of the material. And then the plan for restoration, the approach to restoration, has to be consistent with that site. And the outcomes, the expectations, then have to embrace what river systems are. They're dynamic. They're inherently self-sustaining in that they're a set of processes that move sediment around, that vegetation grows and senesces. And the basic idea is the stream restoration approach has to be function over form. And so a formal way of thinking about this is a channel evolution model. And here's an example of one of them from Klur and Thorne. And this is a channel evolution model that has gained a lot of use and application recently because of things called stage 0, which is the stage at the top, the restoration, the cross-sectional picture at the top, which is thinking of what does a river system, what does a channel look like in its completely functional form. And in most cases, we don't know this, don't see this, because we have, over the last couple hundred years, impacted river systems so dramatically that there's very little of this intact form left. But the idea of a channel evolution model really is a simple thought that the process of degradation, and therefore the process of restoration, is a set of, it's sort of a chain reaction. Something is disturbed. So looking at the going from stage 0 to stage 1, what has been lost is that multi-threaded nature. And so the stream channel has been simplified such that you disturb the transport deposition process, and making it more of a transport reach, which will cause downcutting, because you've concentrated the energy from multiple threaded channel into a single threaded channel. And the only way then to reverse that, to go from stage 1 back to stage 0, is to allow the channel or allow that reach to move from that transport or more erosional state to a more of a depositional state. And that means allowing or forcing, so the actions that are done are going to take the concentrated flow of a single channel and allow them to become multi-threaded. So that's trying to emphasize the fact that channel degradation and rehabilitation are both processes, that both they're not constructing. You might construct an action, you might do an action, but the action is to, if you think about it in a process space, the action is to trigger a set of processes that are heading in a different direction. So if all of the arrows heading around, the solid arrows going clockwise are a set of degradation processes until you start heading up from stage 6, 7, and 8, whereas the dashed arrows going counterclockwise in stage 1, 2, and 3 are changing those processes, reversing those processes. And so this is the fundamental difference between constructing habitat and doing actions that impact processes to trying to change the evolution, sort of the time history of a reach. So going back to our pictures here of our example of a degraded reach and our example of an intact reach. So what's missing to drive this rehabilitation process? So if we could imagine this in the upper right-hand corner, that reach becoming more like the reach in the lower left-hand, what's missing? What is what processes are dominating on the right-hand side that are not dominating on the left-hand side? And again, not having this engagement process, you can't shout out the answers. You can shout it out to yourself in your office. But to me, the biggest difference between that upper right-hand reach and the lower left-hand, what's missing, is some kind of hydraulic roughness. Something that takes what's dominated a transport reach. So the upper right, this is a trench. Water can move quickly through here and take whatever sediment, whatever vegetation that's in the channel, move it out. Whereas in the lower left, you see there are things in the channel. There's a large beaver dam right in the middle, for example. And as a result, you have multiple channels, multiple pathways of the water, and it's much more of a depositional environment. Even if the gradient is the same and the flow levels are the same, how processes will play out just in transport and deposition as just one set of processes will play out completely different because of some hydraulic roughness. And that hydraulic roughness can be wood, so logs in the stream, so in the upper left. It can be beaver dams, like in the lower left, that are either natural or man-made. And the idea is, how can we do this process-based restoration to develop hydraulic roughness? Can we have actions that are addressing this process in terms of changing the way the water interacts with the valley floor, how water and vegetation interact, and how sediment, whatever substrate is being moved, how that is sorted and stored in the sort of the distance it moves. So I'm going to talk about two techniques: beaver dam analogs, that is building a dam, biomimicry, acting like a beaver or a colony of beavers by building a dam, or post-assisted log structures, that is build a tree that's fallen in. And both of these we call low-tech structures because the technology is hand power tools. Wood that's used is wood that 2 or 3 people can carry. You don't need helicopters or large tonkatoys. As a result, the structures that you might build, so on the right-hand side are 2 examples of a post-assisted log structure, and here are 4 different examples of beaver dam analogs. These look very different from kind of restoration structures that many, sort of the history of restoration, stream restoration, has been dominated by. And again, they're not meant to build a habitat, they're meant to build a structure to change processes in a stream. So I'm going to pause here for questions, and hopefully we can turn the, you can type some questions in, and I will turn on a webcam and answer questions if you've got some. Just a quick pause if you've got questions. There's a couple of places where we're going to do this too. So if you don't have questions, I'll keep charging along.
I don't see any questions, so you can go ahead, I think.
Okay, I'm going to keep charging along then. Okay.
Thank you.
Okay, so so the second poll question is to ask you, have you and your groups done any projects involving this biomimicry, beaver dam analogs, and post-assisted log structures? Okay, so some BDAs, a little bit of BDAs and PALs, and a lot of people planning on it. That's great. There's lots of resources, lots of ways to learn about how to do this, and so it's exciting to hear people thinking about using these techniques. Okay, so just to go back to the process-based rationale for doing these kinds of projects, let's look at just the effect of sort of the processes that are triggered or changed with beaver dams, either natural beaver dams or human-constructed beaver dam analogs, and thinking of these as hydraulic roughness elements in the riverscape. So starting at the top with beaver dams, the up arrow next to each of these little word sets means increase in. So if there's an increase in beaver dams, either because you've built some beaver dam analogs or encouraged beavers to occupy reaches that you're working on changing the condition, because they're dams, because they're in the stream, they are going to obviously have an effect on the flow velocity. So water impounded is slowing down. Water that slows down changes its ability to the size of particles, the amount of material that can carry, so you get bed aggradation. So bed aggradation is going up, that's the up arrow. As the result of bed aggradation going up, you're making more habitat for riparian vegetation. As the bed aggradation goes up, you're raising the channel, you're bringing the channel closer to the terraces or the floodplain, so you're increasing floodplain connectivity, which also makes more riparian vegetation habitat. So you can see that these are feedbacks, and that triggering this set of processes by starting with something simple, like a channel spanning structure that doesn't look like it's very permanent, triggers different processes or processes that are already there. So aggradation is part of a transport deposition process, but you're changing sort of the balance of whether the reach is now a gaining reach for sediment that would have normally moved through. But as a result, you get floodplain connectivity. You can get multiple channels forming as you bring the bed of the channel closer to the floodplain. Water more regularly can access that floodplain and occupy different channels. As a result, the stream power or your stream width for any one channel goes down, and that again changes the depositional environment, that changes the environment for vegetation. It also changes the environment for those structures which could influence. So it's a positive feedback. So the more this happens, the more it happens. And that's just an example of how engaging in process-based restoration is thinking about how do you change these processes, not how do you just build a pool. So obviously putting in a beaver dam or beaver dam analog caused a pool to form, but that wasn't the objective. The objective was to trigger the sets of processes and the change in the existing processes as a result by adding hydraulic roughness. Okay, so however, it's not all fun and games if you are mimicking beaver or actually actively engaging with beaver in stream restoration, because beaver can be pests, right? They can block culverts, which can back water up onto roads and fields, into residential areas that impact infrastructure. They are active foragers on vegetation. So if there's vegetation, whether it's ornamental or orchard trees in the area, beaver love to eat woody vegetation, and that may be an issue for the proximity of the product to human land use. And so as a result, there are many people, many companies, and parts of the federal government that will come to the rescue with lethal solutions to remove the beavers. But in removing the beavers, then we're going back here, they're removing all of the things that beaver and beaver dams can do to change stream processes. So if you're going to do beaver-based stream restoration, anything that might encourage beavers either actively or indirectly, you need to have a suite of actions at your fingertips to deal with it. So there's conservation, promotion issues in terms of engaging with how to maintain populations, and that's engaging with state and local entities for either addressing lethal removal or trapping closures, for example, in whole watersheds. There's many methods, and we'll talk about a couple, for living with beaver that is allowing beaver to be in your restoration area. Translocation, if you want animals, it's bringing animals from problem areas or problem animals into areas with suitable capacity, and as well as restoring riparian vegetation, which is making food for beaver, so then understanding how you have to protect that. And then the last things that we've already been talking about, which is sort of mimicking the beaver dam building in streams with beaver dam analogs, as well as the hydraulic roughness elements that BDAs and PALs present. So poll number 3 is, have you and your entities, your agencies, engaged in any of these other forms of beaver-based restoration that are either direct or indirect, as you have beavers in your watershed, in your restoration areas? Either you're encouraging them or you're trying to work around them. Okay, great. So a little less than half of you have engaged in some of these things, some translocation, which is great. That's very ambitious. Beaver deceivers and pond levels, there's some pictures of those in a second, as well as other things. And so be good to find out some of what the other category are items. Maybe you can type those into questions, or we can talk about those at the end. Okay, so just quick pictures of a couple of those the strategies that had directly on the poll. Culvert protection, so beaver deceivers. These are simple fences that are built on the upstream side of culverts. So culvert is a pinch point for streams, and these are obviously examples of undersized culverts. So the biggest issue here is an undersized culvert. The Beaver are taking advantage of the undersized culvert and saying, if I just can dam this mouth of the culvert, I can take advantage of the fact that there's this road bed, this road prism here, which allows me to make a much larger pond than maybe they would have otherwise. So how do you protect that culvert mouth then? Well, it's really just as simple as keeping beaver away from it. And these don't actually have to be, the fences don't have to attach actually to the bank. They need to be enough of a deterrent. It needs to be large enough that the flowing water sound here is less of an attractant to the animals to say that there's something to dam. The large area like this allows a lot of debris to rack up, but still let the water make its way through the culvert so that this caging around the culvert mouth doesn't become just as much of an issue as any kind of debris accumulation in the culvert mouth. And these are really, really effective. They're cheap and really effective when beavers are focusing on a culvert and when culverts are undersized. Pond levelers. So here's another way of thinking about having a pond and not allowing the pond size to grow. So the pond size grows as beavers add to the height and the crest elevation comes up and the water spreads laterally. And that's what beavers do naturally to make more habitat for themselves. So here's the crest elevation of this dam. If they wanted to get at some of this vegetation over here, or they needed a deeper pond, they would add to the crest elevation by having an intake. So this intake is sunk in the pond upstream of the dam and connected with a pipe that then allows the water to drain up and over. And the crest elevation is set by the bottom of this pipe as it passes over the dam. And even though this running water and this crest elevation control are close by, having this perched like this, it's hard for beavers to actually dam it. They're also not triggered to think about how to address this flow issue as opposed to leaks in the dam. And this is a really, really effective way of regulating the height of a dam, which is it's sort of in the living with beaver strategy that you're allowing a pond to exist, but you're not allowing the beavers to change the extent of the pond. And so here's just a high flow event where this structure, the dam is being overtopped, the water's moving around it, and it can the structure itself can maintain those flow events, and even at and then function here is just functioning as the only outflow of the water to allow this pond elevation to be maintained. So those are just two examples. A third example is caging vegetation. We talked about beavers' habitat of eating trees. Here's cottonwoods that were caged as when they were first planted. This is not a great example of caging, and here's the reason why. Is eventually the tree grows to the size of that cage, and in this case, even beavers piled up material on the edge so they could climb up over the cage and then cut down the tree. So this is a good idea in terms of caging. This is a poor exercise, and I call it caging with quotes. Poor implementation of that because animals were able to figure out that there was food inside the cage and then figure a creative way to get to it. If the cage had been set back farther, that would have been fine. Or if there were more trees in this area, so in a sense, having a standing crop of vegetation, they wouldn't be so focused on the few cottonwoods that are in this entire reach. And the last is just an example of translocation. And here's a project that was done on some private ground in Birch Creek in Idaho. The landowner wanted beaver back on their property and went through a translocation process to bring 6 or 7 animals in, built a few BDAs, and in less than 2 years, this is now a beaver-dominated landscape with more than 140 dams. And you can see here's the old channel, this blue thin line, and then here in 2 years, the dashed line is the valley bottom, in the sense the water extent now. So this is what we call a beaver-dominated landscape. They have fully taken control of the hydraulics of this stream system, and it was triggered by bringing animals in through translocation, and then giving them jump start by putting in a couple of artificial beaver dams to get them beaver dam analogs to get them going. Okay, so to do any of this kind of work, you need to do it in the right place. So we talked about the process-based restoration. So the four key things to think about are: is there enough water to maintain a pond? So if this is in any way you want beavers involved in the restoration, then you have to make habitat suitable for them. Is there enough vegetation, enough food, both to support their foraging as well as dam building, realizing that in lower elevation, warmer areas, they do not need woody vegetation. They can survive off of emergent vegetation, cattails, in a sense, grazing on just green, non-woody vegetation. But in places where they do need to make food caches through the winter, woody vegetation is necessary for their diet, but certainly it's necessary for structures for dam building. Can they build a dam at low flows? That is the stream or river too big? They're not going to be able to build a dam, and then those dams likely withstand typical floods, or like the 2-year recurrence interval. And there's some nationally available sort of GIS level information to get at these questions, right? So with the stream network, the 1 to 24K perennial network gives you an idea about where there's a minimal sort of set amount of water. There are vegetation coverages, so things like land fire, and then USGS, either from gauges or building regional curves for your watershed, you can get some base flow statistics to get at what's the sort of the base amount of information, and estimate Q2, the 2-year return interval flows. And the stream, and using DEMs, estimate the stream power, which is just the precipitation in the stream and the catchment area, as well as the local slope. And there are some sort of rules for how to take these characteristics and estimate the dam density, or whether you expect dams to be there at all. But these are the 4 questions that you need to ask yourself if you're engaging in a site that's going to be either supporting beaver dams or using beaver dam equivalents, or that biomimicry. Is that the right kind of tool to change the processes there? So let me just dig in a bit more on these 2 structure types. So BDAs is building a dam, and PALs is post-assisted log structures. So a BDA is a really simple thing. It's just fence posts, a non-treated fence post 3-4 inches in diameter, driven into the stream bed. The height of those posts sets the crest elevation of the structure that you're building. The material that's made up of it is local material, just willow, or we've used juniper or sage brush. You may not need a little rock or mud at the base to seal up if you want this to function at low flow. The spacing and the depth of the posts really depends on the stream flow, but on the order of 20 to 50 centimeters apart, and probably probably 50 centimeters max for trying your full height of the structure. And running, if you want the structure, the channel to start, if you're impounding water and you want that effect to spread out, then run. In this case, it's this being built in a trench. But if you're closer and your crest elevation is near the floodplain or above the floodplain, running your post lines out onto the floodplain is also appropriate, so that you're really not just the water's not getting up and going around, unless you're trying to cause an avulsion event, which is another thing to do to trigger changes in stream processes. Here's just 4 names of different types of beaver dam analogs that we've given. You can do this in any combination. There are manuals to help you think about it, but certainly there are no rules. It's just your creativity. Basic starter dam just sets a post with a little bit of material in them. You can see it's immediately starting to impound water. In some cases, you might think of just putting in posts and letting whatever debris accumulate, so that this would not be immediately acting, but it would act as high flow events move stuff around. Actively weaving in material, in this case willow, to immediately making a dam. And in some cases where you've got existing dams or abandoned dams, adding posts to existing dams can reinforce them and add to their lifespan. And here's just an example of one. This is in the lower John Day in Bridge Creek in Central Oregon, a sort of a starter dam kind of an approach, and a lot of material has racked up on it as well. And you can see that it's impounding water. Post-assisted log structures, building a trees, again, the same kind of technique, using a handheld post pounder, driving posts into the substrate. But the idea here is rather than build a structure that's acting like a dam, it's building structures that have other purposes, and really just the same purposes you would put anything like wood in a channel. But in this case, the wood is not going to stay there without a little bit of help. And so it's really just being pinned. So these are pieces of wood that you can carry. This is wood that's salvaged nearby, or bringing stocking material in, and then pinning it down to the substrate, either attached to a bank or in the middle of the channel, in a sense to put some hydraulic roughness into the channel. So here's just two techniques, and here's some examples of those. So here's a channel spanning wood structure. It's not meant to impound water, but it's meant to catch things that might be moving down or cause flow to deflect around this channel. Here's a bank attached one it's strongly attached on one side, but leaving a little jet over here, which is meant to do erosive work. Here's a structure in the middle that's meant to split the flow. And then here's, in a sense, taking some of that material and just putting it in the channel, a place that you want it to be recruited nearby. So I'm going to pause here, see if there's any questions. You type in questions, and then otherwise I'll keep going.
I'm still not seeing any typed questions, but if anyone would like to raise their hand. Okay, no raised hand, so you can keep, oh, right. There's one. Sorry, I missed it. So, Crystal Morris, I'm going to unmute you. Okay, Crystal, sorry I took a second, but you are unmuted now.
All right, I will charge ahead. If questions pop up, just let me know, and I can pause.
There are a couple questions that just popped up. I'm sorry. There's a lag. Are you ready for questions?
Yep.
Okay. So in the lower left corner of the previous slide, what is the equipment they are using? What is the equipment they're hauling to build the PALs?
Okay, great question. So in building these the PALs and the Beaver Dam analogs, in every case we're using a handheld hydraulic post pounder. And so in the middle picture, the person is holding the post pounder head itself, which has the impeller to drive the post. And what the two folks in the lower left are doing is pulling the hydraulic, that's the power pack. And this is generic equipment. The power pack runs, is portable-ish, they weigh 200, 300 pounds, but they have wheels. So 2 or 3 people can drag them around. We put them in canoes to float them down the channel so you can work. And the power pack needs to be within about 40 or 50 feet of the post pounder. But this does mean you can work far away from roads, as long as you can move this equipment around. You can do this by hand, completely hand, with a slide hammer or a sledgehammer, but in any kind of cobbly substrate, having the extra oomph of a hydraulic post pounder is great. There are gas-powered post pounders, so there's a single unit with a small 2-cycle gas engine that has the same impeller structure. Those are nowhere near as powerful as having the hydraulic unit. What's even more powerful is a pneumatic, so an air compressor driven one, but that needs a trailered compressor. So then you have to be near roads. You can run 200 plus feet of hose to run a pneumatic post pounder, but that still limits you to be near roads. And those pneumatic ones are open circuit, so the whatever lubrication oil is in there gets spit out into the stream. So you have to be really careful that you're using inert oil, whereas the hydraulic postpounder is a closed circuit. The hydraulic fluid, you can use biologically inert hydraulic fluid in case it leaks, but it is meant to be closed and therefore not leaking into streams. Hopefully that answers your question.
Great, thank you. There are a couple other questions.
Yep.
One from Jim Brick. Can you touch on the number of BDAs that should be used and the distance between the BDAs?
Yep, that's the next section right here. So I will hopefully answer your question, but let me know if you still have more questions about it.
There are a couple other questions. Should we come back to those since Jim's question is?
Yeah, you go ahead. Just in case we don't have to back up too much on the slides, we'll try to quickly do that so I can get through. I don't have many more slides. I'll show you some more pictures of implementation of these.
Great. Is there a preferable reach type to place the structures? Glide, pool, riffle, and/or a preferred gradient?
Yep, those are good questions. I will say I'm going to let that slide a little bit so see some of the pictures and some of the rationale when I talk through the design. But any place that you would think a stream impairment exists because there was wood or beaver dams or something in the stream is appropriate. So from 0.5% to 8%, in terms of gradient, certainly are places where we've worked. You get really, really low gradient areas. You're not doing a lot of sediment sorting by changing the hydraulic roughness because there's not a lot of energy. So there tends to be, 0.5 to 1 to 2% is most of these areas, but certainly steeper areas are possible. Wherever you can imagine beaver dams or wood doing work, then it's appropriate to do work like this. And then the reach characteristic, that I'll cover that in a second.
Okay, the final question is about design, so maybe you'll answer this one too. Can you talk about design considerations in building analogs or PALs while maintaining fish passage?
My quick answer is fish passage should not be an issue. I know there are regulatory agencies that say that there are, but you can imagine these structures here that on the screen, those are not channel spanning. And then, sort of the throwaway answer, which unfortunately is not enough for some states, it is for some states, is that beaver and fish of all species have coexisted in our landscape since the glaciers left, so that's 20,000 years. And therefore, if you are properly mimicking beaver dams or log jams, you are not causing fish passage issues. Certainly not fish passage issues in a long enough time span, either within a year or over years, that should have any meaningful issues. I realize that some regulatory agencies or parts of agencies don't entirely agree with that, but from a biological standpoint, beaver dams are not fish passage issues. But let's fight more about that later. Okay, so the structure construction, both for BDAs and for PALs, density and extent. So this just gives you an idea of this picture looking upstream here. The kind of stream, oversimplified, straightened channel, over coarsened bed material for what you'd expect here are all classic signatures of simplified system that is higher transport capacity than it should. And so hydraulic roughness is a perfect tool to try to bump that stream and those stream processes into more of a depositional and more of a multi-threaded or at least a wandering channel. And so you can see the kind of, in the system, you can see the kind of density that was appropriate. These are, 20, 30 meters apart. And here's an overhead shot so there's 1, 2, 3, 4, 5, 6, there's another one here, 7 that are seen from this overhead photo. These are less than 50 meters apart. And so the idea is where you'd expect something in that channel or that kind of that kind of density, that's how these are going to be effective. They're very sort of short-term effect. They're going to cause an effect just immediately downstream, and so you're going to want another one that causes an effect sort of within the shadow. And I'll show you some pictures of that. So the kind of things you want to do, you're really just letting the water do the work. And this is the name of a book, a group of folks working in the southeast, in southwest, sorry. I think it's a great phrase for what you're trying to do in process-based restoration. And in this case, here's a bank-attached post-assisted log structure. So it's attached on this side, and the point was to have a jet sort of channel the flow to the jet. There's a cluster of willows, alders here that were nearly in the channel, and this caused them to be undercut, and they fell into the channel. So it's wood recruitment by doing a little bank erosion. And so when this channel gets too entrenched with alders, it often happens, the stream is straightened, doesn't have the power to engage with the bank. By deflecting the stream into the bank, you can start causing lengthening of the channel because you're going to be meandering, but you're also recruiting material to the channel that will add to that sort of your set of structures in the channel. Here's another example of trying to recruit, in this case, recruit sediment. So here's a cut bank with plenty of material that's the right size to stay in here. If the stream energy was a little lower, the intention of this structure here is to cause to start carving away at this bank to recruit this material so that you can start storing it in the channel, and you store it in the channel with these structures. So here's two structures, so they're close together. This is one storm cycles. This lens, this gravel bar here, gravel cobble bar, is one storm cycle's worth of deposition. Now that you've given some kind of hydraulic shadow in the stream. So again, a very straightened, over-coarsened stream has no way for this material to do anything but transport it down. You can start building bars, which builds habitat at different different elevations of the stream, but also starts lifting the stream bed up if you have incision. And the only way you can do that is by causing sort of depositional environments. And you're causing them on a very local scale, which is why you need many of these things to act together. And the same kind of thing happens with other material that's moving, so wood and substrate that's moving. This is just pinching off the channel a bit, and has caused a capture of material that was naturally moving down the channel. Now, these structures look pretty flimsy, and so you might imagine that they are just not going to last. And so here's some data. This is from the Asotin in southeast Washington. Nearly 600 structures that were put in over 4 years, and in 3 different parts, 3 different treatment areas, and about 50% of them are completely intact after 4 years, 3 or 4 years. Mostly intact and completely intact makes about 70 or 80% of the structures. The remaining 20, 30%, some of them are gone, 10% or so of them are gone completely. Another 15% of them or so are in a sense damaged, they're partially intact. But notice that material from all of these categories here didn't just get washed out into the snake. It, in some cases, forms new structures. So of these, so if we look at sort of 70% they're completely or mostly intact plus new structures, after 4 years, anywhere between 3 and 5 years for nearly 600 structures, around 70 to 80% of them are still there and still functioning. And even the partially intact ones are still functioning, which is pretty good when you're building something that looks like this, and you can build 100 plus of these in a season. You can actually start making a big difference in a stream. Okay, and the same kind of thing with BDAs. So BDAs we sort of brought this idea of BDAs in for addressing channel incision. This is Bridge Creek in the John Day in Central Oregon. In 1993, BLM moved grazing off the land to deal with channel incision. Nearly 20 years later, the channel was just as in size, if not a little bit more, but there was willows coming back, but not anything to change the processes of impairment. Beavers are in the watershed, but there's not woody vegetation, so their dams, these are all breached beaver dams, so their beaver dams were not acting as hydraulic roughness elements for a long enough time, and they're not durable. So in an experiment, we put in 120 of these BDAs in 4 1-kilometer reaches, And not only did the Beaver dam, the BDAs that we put in, but the beavers in the area, so there were 22 dams, active beaver dams before we started. After we did the treatment, there were 164. So not only were there the 120 of dam mimics, but there were another 100 plus dams that Beaver had built because we were giving them a more favorable environment. And as a result, the combination of all those things did what you'd expect it to do. You're inundating floodplain that normally would not be accessible because you're recruiting sediment. All this fine sediment here, for example, is being stored rather than moved down to the John Day. The water table, we had monitoring the wells. The water table was moving up on the order of a meter. And then just your overall planform impact. Here is a single threaded channel before the treatment, and here 10 years later, after the treatment and after beavers have taken over, you're hard pressed to say what's the foul leg in here. And that's a much more natural condition for this reach. And that was taking it from a process that is dominated by transport to a process that's dominated by deposition. And so in a sense, triggering that by adding hydraulic roughness. So to wrap up, because we're right about the end here, the take-home message here is building for function, not for form. Even though these things look like they're not very durable, it doesn't take a lot to trigger these processes. If you've got wood or sediment to recruit, a little bit of roughness in the channel will go an enormous way. And if you are actually recruiting beaver as well, it has that added benefit of bringing in a maintenance crew. And so, a couple of things that are resources I said for design and other questions are this beaver restoration guidebook that we put together, as well as this new low-tech process-based restoration, which goes into many more details on design specifications for both BDAs and PALs. Both of these are available online, and the URLs are in the handout. So I'm going to stop there so people can get on with their day or ask questions. I'm happy to hang out as long as there are questions.
Okay, any last questions? I'm not seeing any hands raised or new typed questions, just a thank you. So thank you to Dr. Jordan for the excellent presentation, and thank you all in our audience for joining us. If you have one more minute, I have a question.
Yep.
So this is relying on kind of kicking off a multiple processes from a pretty simple change. So I was wondering if you have any tips on communicating about predicted outcomes to landowners or on grant applications. How do you kind of keep expectations reasonable, but don't underestimate yourself too much?
Yeah, that's a really good question, because there's a very long list of impairments that you can address with either of both of these techniques of putting hydraulic roughness by hand into channels. And you really need one way to answer that is to look at an individual structure. So let's just go back to these here. You need to have a plan on a structure by structure basis for what you expect the structure to do. And these structures, as I said, they need to go in concert. They don't work alone well. They work well when you put in a number of them. And the analogy is with beaver dams. A beaver colony rarely makes one dam. They usually make a number of them. So we put in BDAs as a complex, 5 or 6 or maybe up to 10 in one area, and that acts the same way a beaver colony would in that reach, maybe 500 meters or so, up to a kilometer. And so you have an objective for each of these structures, and you have an objective for the complex. And so here, the objective is to recruit sediment, and that's individuals and as well as the entire complex. Here, this structure, this recruiting sediment was recruiting sediment that's in the channel. This structure has the objective of recruiting sediment from the bank. And so if you want to then have monitoring, you can use simple photo points to say, just looking upstream, say, okay, have I actually recruited any sediment? Or here, on this one, you're very easy to say it's successful, that this structure did its job. It's easy to see this structure hasn't done its job, but you also understand that whatever sediment was moving down was recruited by this one, and there wasn't any left by the time you got here, right? And so as this fills up, now this one is going to start having that hydraulic effect that this one did. So that's why you have to have them in sort of a high density, and that's why you think about them all together. Now, there are lots of other things that are going to happen as a result of this, but sort of your simplest response that you can talk about, that you can design to, is sort of that first order response. What are they going to do initially? Rather than saying, okay, eventually this is going to cause channel aggradation, we're going to recruit this vegetation, we're going to get channel lengthening. All of those things can happen, and that's all the processes that are triggered. But I would focus on what your immediate expectation is, because these tend to be fairly quickly acting responses, and that it's going to trigger a longer change in the channel. And so this example here, where we looked at over 10 years to see this before and after, that was not immediate. That did take 10 years for this channel to slowly degrade, to start activating other places, for beaver to come in. And so our goal initially was channel aggradation in this channel, hoping that we could get to this point, not imagining it would happen in less than 10 years, but not saying that this is what our final objective was from the implementation. Implementation at each project was aggradation and making the water more likely to engage with the floodplain. That happened, but that happened after multiple steps. So I think it's biting off each piece as you go in the design and your assessment, and having that bigger picture goal of a long-term part of the project, but you have a short-term response that you're arguing for and watching for.
Great, very, very helpful answer, I think, and I hope everyone else found it helpful too. With that, I will close down the webinar. Keep an eye out for the recording. I'll post it tomorrow afternoon, probably. And I hope you all join us for the next webinar, the third Thursday of July, on OWEB grants from start to finish. Thanks again, and take care.